on your chat. Also, you can check our calendar, future events, and all previously recorded talks on our YouTube channel. Please bear in mind that our talks alternate between Thursdays and Fridays. And finally, if you wish to be added to the Google agenda so that you never again miss a talk, you can mention that in your email. You can say, please add me as an invitee to the event, and then it's going to be added automatically to your agenda. That's the easiest way of doing this. So without further ado, very happy to have our colleague Anna Fino from Università Torino telling us about balanced metrics in the Hull-Strominger system. Anna, we're doing 50 minutes, so at 5:02 we stop for questions, and then we can lag on a bit later. Also, everybody, please have in mind, Anna will probably not be able to see you while she's presenting, so please just interrupt, okay? Or if you're too shy, you can type it in the chat and I'll interrupt her for you. All right, please, Anna, go ahead.
Okay, so first of all, I want to thank very much the organizer for the opportunity to give a talk in this nice seminar series. And today I will talk about balanced Hermitian metric, in fact, and the Hull-Strominger system. So the idea of the talk is starting from definition and general property about balanced Hermitian metric. And also I will discuss a little bit a conjecture that relate this type of Hermitian metric with other type of Hermitian metric. And in the second part of the talk, I will talk about solution, some non-scalar solution that we construct jointly with Luigi Vezzoni and Grantcharov of the Hull-Strominger system. So I will give some introduction to the Hull-Strominger system, starting from physical motivation, and then a review of some known non-scalar solution, in particular the Fu-Yau solution. And we will see how we generalize their construction, changing essentially the basis. So instead to consider K-free surfaces, we consider a K-free orbifold. So let's start. And let's start with the definition of balance metrics. So we will work on complex manifold, and let's suppose our complex manifold is complex dimension n. A balanced metric is an Hermitian metric. Here I will identify the metric with the 1-1 form, the fundamental form associated to the metric. And we ask that if we do the wedge product of omega n minus 1 time, this is closed. So essentially what we are asking is the existence of a D-closed n minus 1 and minus 1 form. There are very nice characterization of balanced Hermitian metric. One is due to Duchamp and is related to the Laplacian related to the operator del, the operator the bar, and the usual, the Laplacian, I would say, operator. And in fact, one can see that the metric is balanced if and only if one take any smooth map, then the Laplacian with respect to del of f is equal to the Laplacian with respect to the bar of f, and is 2 times the usual Laplacian. And very nice characterization, and in fact is another way to define the balance condition is due to Michelson in terms of currents. And Michelson showed that the compact complex manifold admits a balance metric if and only if M has no positive current of degree 1-1, which are components of a boundary. That means, what does mean? That it cannot resist positive currents T of degree 1-1, such that there exists an S, current S, such that your T is ds plus d bar of S bar. And this gives a nice abstraction to the existence of balance metric in terms of compact, complex, and manifold. In fact, M, if it has a balance metric, cannot have compact, complex, submanifold of codimension 1, homologous to 0, of course. And this applies, for instance, to Calabi-Ekman manifold. So the product of two odd-dimensional spheres cannot have balance metric. And that's follow essentially using the torus fibration over the product of the complex projective space. And this torus fibration over this base, in some sense, inspire the general construction of Goldstein and Upstein that we'll see later and were used for Fu-Yau, from Fu-Yau. So in some sense, a torus fibration over Kähler manifold in this case, they have no balance metric, but if you change the basis in a nice way, you can get nice construction of balance manifold. What about example of balance metric manifold? If one start with a 4-dimensional oriented antiset dual Riemannian manifold, and you take the twistor space, so you take the bundle of almost complex structure which are compatible with the metric, the Riemannian metric, and with the orientation, that's always have a natural balance metric that was shown by Michelson. And another way to construct a new balance manifold is to use that, in fact, the balance condition is invariant by bimeromorphic. So Alessandrini and Bassanelli show that if you start from a compact Kähler manifold and then you apply bimeromorphic, then you get a compact complex manifold which is balanced. And that gives nice example like Moyezon manifold, which are in fact bimeromorphic to projective manifold, and they have algebraic dimension equal to the complex dimension, and the complex manifold in the Fujiki class C, which are again bimeromorphic to compact Kähler manifold. A natural, also nice construction, very easy construction of the compact balance metric is starting by using Lie groups. You consider a unimodular complex group. So in this case, the complex structure is bi-invariant. And let's take any left invariant, Hermitian metric, then automatically is balanced. And this was shown by Abben and Grassi. And so it's easy to construct compact manifold. Just take the compact quotient of your unimodular complex group by a lattice. And then you get what is known in the literature, the complex parallelizable manifold. And with Grantcharov and Vezzoni, we study more general the existence of balance metric on a class of compact homogeneous space, which are complex homogeneous space with invariant volume form. What does it mean? It means that you have a compact manifold with a complex structure and the volume form, which are both invariant by a transitive action of a Lie group. And what we could characterize this manifold, which are not complex parallelizable. So here we are considering torus fibration over a product of, in fact, a complex parallelizable manifold and a rational homogeneous manifold. And so we exclude the complex parallelizable case, and we show that in particular, the first chain class has to be different from 0. Let's see now the interplay with other type of Hermitian metric. The first thing that one can show was shown by Alexandrov and Ivanov, and with another proof by Dan Popovici, that if you take Hermitian metric, which is on the same time balanced and pluriclose. What does mean pluriclose? It means that the fundamental form is the D-bar close. Then automatically the omega, your fundamental form, is closed. So you have a Kähler condition. And we conjecture with Luigi Vezzoni this property that in fact is true. We have many evidence for many family of compact complex manifold, and is the following. Every compact complex manifold which has a balance and a pluriclose metric is automatically Kähler. Now I will report some manifold for which this property, this conjecture is true, fact. The first is exactly the twistor space of a compact anti-cell dual four-dimensional Riemannian manifold that was shown by Misha Verbitsky, and also for compact complex manifold in the Fujiki class. The conjecture is true, and that was proved by Kyose. And also for this nice family, let's say, example that were constructed by Li, Fu, and Yau using conifold transition. Let's apply this conifold transition to Calabi-Yau manifold, and they show that in fact the balance condition is preserved. So if you do a conifold transition, so you do a contraction, and then you in fact you do a smoothing, so you consider a small deformation of the complex structure that makes the family to be smooth. I am speaking not maybe really roughly, let's say, but anyway, what they get connected sum of k copy of S3 cross F3, and what they showed, in fact, that this example is no pluriclose metric, even if this is satisfied the Dibble lemma and so on. So it seems that there are some chances probably that this conjecture is true for all compact complex manifold. And then I report some results that I got with Vezzoni, natural example of compact manifold admitting pluriclose metric are given by two steps in manifolds, so compact quotient of an hypothetical group by lattices, and with invariant complex structure. So the complex structure comes from, let's say, left invariant complex structure on the Lie group. We show that in this case it's true. We also show that it's true in complex dimension 3 with invariant complex structure with holomorphically trivial canonical bundle. Also in this case it's true. And recently with my student Fabio Paradiso, we are looking this more general in almost abelian Sol manifold with invariant complex structure. What is almost abelian Sol manifold? You still take a quotient of a solvable Lie group by lattice, and the solvable Lie group is very close to be abelian because in some sense it's a semi-direct product of R times, let's say, R 2n minus 1 is 2n is the real dimension. And even in this case, that they give a very rich family of compact manifold with pluriclose metric. Even in this case, the conjecture is true. So let's go to the Hull-Strominger system. I hope that I will say in the correct way the physical motivation. Mario, please correct me if I say something wrong. Anyway, in some sense, we want to describe the geometry of compactification of a theoretic superstring with torsion to four-dimensional Minkowski space-time. So what is this compactification? We want to have a link from a 10-dimensional manifold to four-dimensional Minkowski space-time that in fact is flat. And what we can do is in some sense to set to zero the semionic part and only to write down at the beginning the bosonic part. Then one write first the bosonic part of the theoretic superstring action, and then compute its critical points to get the equation of motion. But we will see that in fact, with the Hull-Strominger system, we only get part of the equation of motion. We need an extra condition that I will explain later to have all the equation of motion. And also I want to say what are the bosonic fields. The bosonic field is a Lorentzian metric in 10-dimensional, is a strength field, which is the flux. In fact, is the torsion, let's say, 3-4. And then the dilaton, which is a function, and the gauge connection. These are our bosonic fields. So the geometric object that we are considering is 10-dimensional Lorentzian manifold, which is a product of four-dimensional space-time, and the compact 6 manifold M6. And then we have a gauge bundle E over our compact manifold with a gauge connection. So the idea is to, in some sense, to link from the 10-dimensional Lorentzian manifold to the 6-dimensional manifold, the compact manifold. Okay, so locally, what we have, that our 10-dimensional manifold is a product of M4 and M6, and M6 is a 6-dimensional compact space. And we will consider as 4-dimensional R1 free, and we want to reduce all the equations required by superstring theorem to geometry of M6 and on the vector bundle, the gauge bundle. Okay, on this product, we can have two types of metric, the product metric or the warping product metric. When we have a product metric, this is the compactification without flux. The flux is 0, found by Candelas, Horowitz, Strominger, and Witten. And in this case, as I say, we have a product metric. The gauge metric is just a spin connection, and the bundle is a tangent bundle to M6. So in this case, M6 has to be Calabi-Yau, free-form, with Keller-Ritchie flat metric. And the existence of a solution in this case, so the existence of a Keller-Ritchie flat metric is exactly the Yau theorem solving the Calabi conjecture. In the case when the metric is not a product, but is a warped product, so we have a warped term factor. This is the case when we have flux. So the flux is non-zero. And in this case, M6 has to be Calabi-Yau free-form in the sense that the canonical bundle is holomorphically trivial, but our M6 is not anymore Keller. Okay, now I describe exactly what are the equations for the Hull-Strominger system. So we want to identify string vacua, which are still space-time supersymmetric. And independently, Hull and Strominger essentially formulate this system, this equation in this way. So let's consider M a compact complex manifold, a complex dimension free, and which admit a nowhere vanishing holomorphic free zero form. Let's call big omega. And let's consider a complex vector bundle, E over M, with a Hermitian metric, H, along its fiber, and a constant. We will be slot parameter alpha prime, real number. Okay. So what is a Hull-Strominger system? So it's involving the Hermitian metric omega on M, and also the Hermitian metric H along the fiber, okay? And in particular, the first equation is involving the curvature of the chain connection associated with the Hermitian metric H. And here we view essentially the FH, our curvature form, as a 1-1 form with value in the endomorphism of E. Okay, that's the first equation. The second equation, we ask, in fact, we will see later, not that omega is essentially closed, omega square is closed, but we ask that the conformal change of omega square is closed. In fact, what we ask that if we take omega square and then we take the norm of the free zero form, big omega, with respect to omega, then we ask that this new 224 is closed. And that corresponds exactly to the conformally balanced condition. So a conformal change of our metric is balanced. And then we have the third equation, which is a more important one, we'll see also later. And this is coupled, in some sense, the curvature of the chain connection of H and a curvature of here a right metric connection nabla, but in fact, you need an Hermitian connection. So the connection has to preserve the metric and also the complex structure. And again, here we consider R nabla essentially as a form with value in endomorphism of T10. this time. So the equation is in some sense coupling the two curvature, and then the more important equation for Hull-Strominger system. So if you remember what happened with the zero flux, in that case, the metric.
Anna, can I ask you a question?
Yes.
Just
sure.
before you go on. So about the, if you can go up one, please. Just go,
Before.
So no, on that one, on the heterotic Bianchi identity, on equation 3, right? On condition 3.
Yes.
So the left-hand side should in principle be the derivative of some torsion, right? So can you please explain?
The torsion is something like d minus d bar, I think, of omega, and then if you take the up to a factor, and then if you take the differential, then you just get d bar of omega.
Right. So this is really the derivative of torsion.
Yes. The torsion is something like d. Essentially, is like d minus d bar of omega, and then you take the differential of that. Yes.
Okay,
yes.
So we have the same equation. That's great.
Yes.
That's great.
It's just formulated this way, but it's exactly the same equation.
Great.
Yes.
Okay, cool, very cool. Okay, go ahead, please.
Yeah, no, here it's just that you have a SU-free structure, in fact, right, related to that, and nabla. I will come back later about that. Anyway, nabla for the moment, let's say that is any Hermitian connection. In fact, it can be any connection in Goudouchon family of Hermitian connection, but in the construction that I will give in this talk at the end, I will use a chain connection, which is not a good connection for physics. I know that. Okay, I will point out later, but.
Okay, looking forward.
Okay, so where I was here. Okay, so what I was saying that in fact, here is a point. When you have a holomorphic bundle of degree 0 and is reducible, and then the equation that I wrote, this equation, I don't know if you can see when I point out, this equation, in fact, are equivalent to ask that our holomorphic vector bundle is stable, right? This was, in fact, this equivalence was formulated for Kähler manifold from Dolanson, Uhlenberg, and Yau. Here we are not using for Kähler manifold, but later was extending this equivalence by Lee and Yau for asking that omega is Goudouchon, not anymore Kähler, but Goudouchon. What does mean Goudouchon? It means that if you are in complete dimension n, you are asking that d bar omega n minus 1 is 0. And of course, balance in particular are Goudouchon. So these equivalents still apply. And one can use this also for orbifold, but one has to be careful about that, because the type of singularity that you have to take, Kähler orbifold, the type of singularity that you have to take are mild. And for this, we use a result by Simpson that in some sense is saying that if the singularity are not too bad, then you still have this equivalence. Okay. As I said,
Anna, can I just say, in the Goudouchon, not necessarily Kähler case, stability is still just slope stability, right?
Yeah, polystable, yes.
Okay.
Yeah.
Slope,
Yeah, slope is involved in the slope. Yes.
Cool. Yeah.
But of course, this notion, since the slope is defined using the degree, then depends on the choice of omega. So the condition to be stable, I didn't say, but of course it's depending on the choice of omega, right?
Absolutely, it's polarized, yeah.
Okay, and why is the generalization of each flat metric? Because coupled with Hermitian Yang-Mills equation, because as we saw already before, Calabi-Yau manifold can be viewed as a special solution. So you just take E equal to T10 of M, and then you take H equal to omega. And then when you write the Hull-Strominger system, you reduce to I, e to the power omega 0, and the differential of the product of the norm of the big omega times omega squared 0. That gives you the norm of the free 0 form, let's say, with respect to the metric is constant, and then omega has to be killer and H flat, so the norm is SU-free. In this sense, they generalize this condition. And what is the length of balance metric? I already said before. So the second equation essentially says that omega is conformally balanced. If you do a conformal change, you get a balance metric. I want also to remark that how Hull and Strominger formulate the equation was not in this way, was the co-derivative of omega equal to I, the bar minus del of logarithm of the norm of the free 0 form. And the equivalence was proved by Li and Yau, and that was very useful because it gave the link with balance metric, in fact. So why I say now the Hull-Strominger system can be interpreted as a notion of canonical metric or conformally balanced manifold, because in some sense you choose a positive 2-2 form, right, which is closed, so give you a cohomology class, and then you impose some condition on the curvature, not only the curvature of omega, because it's coupled with a condition also involving the curvature of, let's say, the gauge connection, right? But it's similar to the situation when you have, let's say, you have a Kähler manifold, so you have a Kähler class, then you have a cohomology 1-1 form class, let's say, and then you impose extra curvature condition, like to be constant scalar curvature and so on. Here the situation is a little bit different, but in some sense we have some choice of a 2-2 class and then some extra condition on the curvature. Okay, as I explained in the beginning, we have some choice here because in fact omega is not Kähler, all right? So you have just an Hermitian manifold, and then you have a one parameter line of natural unitary connection that you can choose, the Gudoshan, in fact, family of Hermitian connection. Every connection is determined by a condition in the torsion. The chain connection, we know that is determined by the condition that the one bond part of the torsion vanishes, and then the bismuth connection. That means that the torsion is in fact skew symmetric with respect to all the arguments. Also, another remark that one can see that from physical point of view, one has that alpha prime has to be bigger than equal than 0, with alpha prime exactly corresponding to the Kähler case. But in mathematical literature, also the case alpha prime less than 0 is also considered. For instance, by Fong, Picard, and Zhang. In the talk, I will consider the case when nabla is exactly the chain connection of omega, like in the case of Fu-Yau solution for the Strominger system. But I want to say that, in fact, this is not the right thing for physics, because if you want to find a solution of the Hull-Strominger system, is not enough. You need to impose an extra condition that was remarked, I think, the first time probably by Ivanov. And in fact, Ivanov showed that the solution of the Hull-Strominger system satisfies the theoretic equation of motion if and only if the connection nabla in the anomaly cancellation equation is an instanton, an SU-free instanton. So the curvature, essentially the curvature to form has to be in SU-free. So you have that is also in Young connection.
Anna, can I just real quick make a point here?
Yes.
That's not entirely accurate. So, right, I've been torturing myself with this very point, just so that if people are watching, on Ivanov's paper, there's theorem 4.1. So there's a second degree condition on the curvature that is necessary and sufficient.
Okay.
It's implied by the instanton condition. So if you have an instanton, you could. right?
Okay.
But it's slightly weaker than that.
Okay, so it's not enough to have R nabla 020 and R nabla wedge omega square 0.
It's enough, but if you don't, it's not the end of the world.
But it's stronger than instant. Okay.
Yeah. No.
Okay.
I'm saying the condition is weaker than instanton. Instanton implies what you need, but you could get away with almost instanton.
Right?
Okay. You could get away with slightly weaker. Yeah, because it's taken me a lot of time to figure this out. So
it's your result.
No, it's Ivanov's.
Ivanov.
He says it, but we don't. I mean, you have to read it carefully.
I didn't realize. Okay.
Yeah, it's Ivanov's. He says it, but nobody paid attention, including myself. So, yeah.
Okay, sorry, I didn't notice. Yes.
Sorry to interrupt. I think he states that the theorem has an if and only if, right?
No.
Okay, but anyway, it's good to know. So it's enough for almost instant. Okay.
Have a look at theorem 4.1 in this paper. Yeah, because there's a slightly weaker condition than.
Okay.
But
thank you. Thank you for pointing it out. I will look again. Okay. Now I will review a little bit non-Keller solution. I hope that I will for sure not citing all the results, so I did a choice. The first non-Keller solution has been found by Fu-Yau on a class of toric fibration over K-free surfaces. And this is exactly the class of example that we generalized at the end of the talk, changing the basis. Instead of considering toric fibration over K-free surfaces, we consider toric fibration over K-free orbifold. And here the toric fibration is the toric fibration given by Goldstein and Prokushrin, okay? And generalized essentially the Calabi-Ekman construction that I mentioned at the beginning. And then there are plenty of non-Keller solution on the groups, and they quotient by discrete subgroup by Fernandez. I want to say that the first non-Keller example, they consider the as connection, nabla, the chain connection. But then there are papers by Fernandez, Ivanov, Ugarte, Villacampa, where they consider also the other connection of in the Goudichamp family, in particular the bismuth connection, I think. And this example they take on SAT are on hypothetical group, in fact, are on the product of the 5-dimensional real Heisenberg times R, and of course they induce solution on the compact quotient by lattice. So our example on company manifold, and then Fei and Yau consider non-Keller solution again, not considering nabla as the chain connection, but different connection in the family on compact quotient of unimodular complex group. And then other example by Grantcharov and many other people, okay? Here I mentioned a very nice construction by Mario Garcia Fernandez using the duality. He found new solution on non-Keller torus fibration over K-free surfaces, which give are very nice because they give the first example of T-dual solution of the Hull-Strominger system, and it's not easy to get that. Another construction was given by Fei, Wang, and Picard, and in this case, they consider non-Keller fibration over a compact Riemann surfaces, and here the fiber is a compact hyperkeller manifold of real 4-dimension 4, and also this gives solution, nice solution to the Hull-Strominger system, and now we see our construction that we will give new simply connected, in fact, example of compact non-Keller solution to the Hull-Strominger system. So let's review the construction of Goldstein and Prokushrin. The construction, we start with a K-free surfaces, S and omega S, and with omega S, a rich flat Keller metric. Okay, then consider a pair of anti-cell dual 114 omega 1 omega 2 on S, which such that here probably I didn't mention 1 over 2 pi, okay, for which the class, the corresponding class, give an integer cohomology class. And then what Gosten and Prushnik did is associate to a toric fibration pi from M with base S with a nowhere vanishing holomorphic form, which is given by essentially the connection theta, okay? There was a real part, imaginary part, theta 1 and theta 2 are determined by the condition d theta I equal to the pullback of omega I, which the pullback of the 2-0 form of big omega S on S, okay? And then what is easy to construct a balanced Hermitian metric because you just take I, theta wedge, theta bar, okay, give you a 114, and you add the pullback of the 114 omega S on the base. And then what you get is a balanced Hermitian metric because if you compute the differential of the wedge square of omega 0, this is 0. What Fu-Yau found is essentially to use this Goldstein-Prushnik construction, and for the metric, for looking for the metric for the solution of the Hull-Strominger system, they use this AmSur. So they modify the omega that we considered before. The part given by I, theta wedge, theta bar is not modified here. They just modify omega S, multiply omega S times the exponential of a function, a scalar function on your base, S. And then if you impose the Hull-Strominger system, what you get is a two-dimensional complex Monge-Ampere equation with gradient terms of this type. Here we have that f is a known positive function, positive in the sense bigger than equal than 0, and mu is a 2-to form with average 0, so with integral essentially 0. And of course, you have a condition for which omega u define a matrix. So under the elasticity condition that is given by the positive of that form. And essentially, the nice theorem by Fu-Yau is that they found that, in fact, there exists a solution satisfying the above elasticity condition, and of course, the complex Monge-Ampere equation. And so, in particular, they show that there exists a solution of the Hull-Strominger system with M, a toric fibration over K-free surfaces. Here, nabla is the chain connection. And the complex Monge-Ampere equation that I showed before, in fact, was generalized one-dimensional by Fong, Picard, and Zhang. And they show also that there are solutions for that case. Here, I was just to mention, I will be very quick, but I cannot talk about Hull-Strominger system without mentioning the anomaly flow, because first gave another proof of Fu-Yau theorem, let's say, but anyway gave many ideas how to study the evolution of balance metric and conformally balanced metric. So in fact, one could try to use the following AmSur that seems to be in principle simple, but is not. If you start with a balanced metric, omega 0, and then if you take any metric omega, which is completely determined by omega square, we know that, okay? And just take omega square equal to omega 0 square, in the sense of wedge, plus I dd bar u of omega tilde. Here, omega tilde can be any 114. This is automatically balanced, and one can then try, of course, to solve for u, for this function u. But what is going on, the resulting equations are very complicated and non-natural. So what essentially Fong, Picard, and Zhang try is to interpret the solution of the Hull-Strominger system as a stationary point of the following flow. Here, in fact, I don't write completely the flow because there is another equation that is involving, of course, also the metric H, which depends on T, and also omega here is depending on T. And here I just change a little bit the notation. So R is just R nabla, okay? And F is just FH, as I denoted before. But what is important here to note that when you start from a balanced metric or conformally balanced metric, if the flow is solution, then the solution remains conformally balanced. And there are many results related to that, but I don't want to talk about that. I want to just mention. And now let's go to the main result of the construction that I want to give. So we show the following with Grantcharov and Vezzoni. So let's take S, a compact K-free orbifold, let's denote by omega S, reticular form, and by ES, the orbifold, Euler number. And now let's take, as in the other construction, two anti-cell dual 114 on S, omega I, such that the class, the cohomology graphs are again integer. And suppose if we take the total space of M of the principal T2 orbifold bundle determined by the omega I, then suppose that is smooth, okay? Now, if we take W, a stable vector bundle of degree 0 over our compact K-free orbifold, such that these conditions are very similar to the condition used by Fu-Yau. Here we just use the orbifold Euler number, ES, okay, involve the Chern class of C2, the second Chern class, and C1 square of S. And what we show that M as an Hermitian structure, omega, I denote with omega U because again we use an x-axis about omega, changing from omega to omega U using a function U. And we show that there is a metric H along the fiber of W such that, again, here as solution we take omega U, so M omega U, that's the conformally balanced metric on your compound killer manifold, let's say, and then you take the pullback under pi of small h and the pullback under pi of W. I want to give a sketch of the proof, just a sketch, so I will avoid the technical part, but just give an idea. The first part is more or less the same like Fu-Yau because the Chern-Weil theory, let's say, can be adapted in this case. So if theta I are the connection one form, such that d theta I is the pullback of omega I, then the smooth T2 bundle, we suppose by hypothesis that is smooth, as a complex structure such that the 1-0 form is just given by theta 1 plus I, theta 2, and we ask for the pi is a holomorphic projection that defines the complex structure, more or less, on M. Then, if we take, as in the case of Fu-Yau, theta 1 wedge theta 2 plus a pullback of omega S, then the condition for this 1-1 form to be balanced is equivalent to ask that the trace of omega 1 and omega 2 with respect to omega S are both 0. And in particular, if we choose omega 1 and omega 2 to be harmonic, then this is equivalent to a topological condition, which is the cup product of the class of omega S with the class of omega 1 and omega 2 are both 0, this cup product. Okay, now of course we need the holomorphic pre-zero form, and that's natural. You start with, let's say, omega S, holomorphic to 0 form on S, which has constant norm with respect to the Kähler metric, omega S. Then if you just wedge omega S by wedge theta, you get a free 0 form on your total bundle, let's say, which is holomorphic with constant norm with respect to omega. And now we can apply the same ansatz. So we look for a smooth function U, And we consider the metric given by U pullback of omega s plus theta 1 wedge theta 2, as exactly before. And we know that this is conformally balanced with conformal factor, essentially what? The norm of the free zero form with respect to the new metric, omega u. And then if you take a stable bundle on S with respect to omega s, and the stable bundle is degree 0, and you take Hermitian Yang-Mill H with curvature of the chain connection FH, then the pullback of this W is still stable bundle of degree 0 on M with respect to the new Keller, let's say 114, omega u, with H, which is Hermitian Yang-Mill, and curvature just given by the pullback. Okay, so this is quite similar to the case. How we show that we have a solution. Here, essentially, we use the Foliati structure of the manifold M. Because if you consider on M the theta, okay, our form, theta 1 plus I, theta 2, and then consider the pullback of the Keller form, omega s, and the pullback of the 2-0 form, big omega s. And then one can show that, in fact, omega b is close. You have the condition omega b, wedge theta 0, and that's important, if you consider the interior product, okay, so you contract your omega b by zeta, where zeta is a dual to theta with respect to the metric, then this is 0. So in natural way, what we have here, that the real part of zeta and the imaginary part of zeta give you a foliation, a Riemannian foliation, but the transversal holonomy of this Riemannian foliation is in fact contained in SU3. So we have a transverse Calabi-Yau structure on M. So what we did, that's the technical part, the analytical part, is to reduce the Hull-Strominger system on to, let's say, a transversal elliptic equation. We use transversal elliptic operator in this case, and we prove in this way generalization of the Fu-Yau theorem to Hermitian free fall with a transverse Calabi-Yau. So it's a little bit more general. In fact, you use, just as I said before, the Foliati structure, okay? And to solve the transversal elliptic equation that we get, we use a result of El Cacimi for transversal elliptic operator. Now, I think I over time, I have still 3 minutes, right? Yes.
You're not over time. You have 3 more minutes.
Ah, okay. So I can present how we get a new simply connecting example. Okay. Here I will avoid to be technical. I will give an idea how we get that. So the idea that we get T2 bundle over an orbifold in this way. You can see that we have a sequence, in fact. Okay, the first from M1 to S will be a safer S1 bundle, okay, and will be smooth. And then going from M to M1 will be a regular principal bundle S1 over M1. Okay, so I will, roughly speaking, now about safer S1 bundle and how we use that. Roughly speaking, so I will not be precise, safer fiber manifold are 2n plus 1 manifold, L, which have differential map over X, where X is a complex and manifold such that, let's say, every fiber is a circle, okay? In fact, the natural setting to consider safer bundle is when the base X is, in particular, a complex locally cyclic, C is missing, orbifold. Then locally, what does mean? That the base is of the form Cn over G, where G is a cyclic group. In fact, we will apply that when G is zeta 2. And the type of singularity will be isolated, in fact, and of type A1 in the Duval description of singularity. Anyway, what is the idea here? Is that if you consider the union, there is a union of Weyl divisor, di on X, such that if you remove this union of divisor from X, in fact, what you get is a circle bundle of X, removing that. I am not so precise here because, in fact, for a general point, what happened here, that the fiber, okay, is no, let's say you have no problem, the multiplicity is 1. Why I call here multiplicity? Because when you have multiplicity bigger than 1, it means that the fiber, in fact, you have the action of main root or unity. And this M is exactly the multiplicity that you assign to every fiber, okay, more or less, roughly speaking. But what is important, that you can determine the safer S1 bundle by essentially what is called the first chain class. Before to do that, what you can do, so you have di, your Weyl divisor, you have for every fiber a multiplicity, mi. So consider this linear combination of di, then what you get is Q-divisor, okay? This is called the branch divisor of X. And this is a very nice, important result by Collard that say essentially you can, if the important thing here, that if the base, let's say, is trivial, H1 orbifold, okay, then everything your safer S1 bundle is completely determined by its first chain class. And now we define that this. Okay, this class representing B is just a linear equivalence class. So you are using the identification with the dual Poincaré 4, okay, of B. So it's a class of B, in fact. B is a Weyl divisor of X. And then you have extra number, Bi, which are smaller than Mi and relative prime to Mi. What we did essentially to construct simply connected example is to construct two different Q-divisor such that the first one, essentially both, give our fibrillation that we want and simply connected, roughly speaking. And now I say you exactly what type of basis we consider is very simple. We consider a Calabi-Yau orbifold surfaces, S, which is just given by the intersection of 2 degree 6 hypersurfaces in the weighted projective space, 2, 2, 2, 3, 3, in generic position. So what we have, in fact, that our S has isolated singularity of type E1, that means that correspond to zeta 2, as I said before, and the fundamental orbifold, fundamental group of X, that's very important for us, is trivial. And then, okay, here first I give the construction, not simply connected construction, but this in some sense is a simple one, because what we did is to blow up S at 9 minus k point, where k is between 1 and 8. So we just did some partial resolution. And then we construct a smooth, safer S1 bundle over S. And then we apply the main theorem that I described before to just a product of this smooth, safer S1 bundle times S1. And what is important here, that the 5-dimensional manifold that we get as a semi-free S1 action, okay? And then we can use the Barton result and the Collard result to show, to identify which M1 it is. And in fact, is the connected sum of the product of S2 times S3. Sk, of course, is related how can be the second battery number when we blow up. Okay, starting from 24. Okay, 22, not 24, the B2 of K3 is 22, I'm sorry, okay, I am tired probably. And then we show if K is between 13 and 22, and R is between 14, and 22, on the smooth manifold, on the product of S1 times the connected sum of S2 times S3, and the connected sum of S2 times S4, connected sum R plus one copy of S3 cross S3, there are complex structure with trivial canonical bundle. Here I didn't explain how we consider the second case, but essentially we construct two divisors to get our structure, and we show that in fact they have a balance metric, trivial canonical bundle, and they have a solution to the Hull-Strominger system. The case K equal to 22 and R equal to 22 correspond exactly to the Fu-Yau solution. And what we have essentially is a principal S1 bundle structure over S1 bundles. And the simply connected case are obtained starting from a K-free orbifold with isolated A1 singular point and trivial orbifold fundamental group, as I say. Here I just want to mention that for R equal to 1, in fact, there is something that is not included in this case, of course, but there is something that we don't know, is an open problem, because if you consider S2 cross S4, connected sum 2 copy of S3 cross S3, this manifold is one of the manifolds considered by Fan and Panov, and there's also a complex structure with a free C star action. And so the natural question is, can have some balance solution that give a solution to the Hull-Strominger system? This we don't know. Of course, the complex structure is different, not considered in this case, but it would be nice to have some result more general for complex manifold with a C star, with a free C star action. I think I stop here. I over time, sorry. And thank you very much for the attention. Sorry that I am over time.
All right, so let's have some discussion. Maybe Mario wants to begin, I guess. He wants to correct something I said, which is marginally wrong.
Oh my God.
Yes,
correct,
yeah.
correct.
All I wanted to say is that what Anna was saying was correct. So the result by Ivanov is an if and only if. So what Anna was saying was fine.
Okay, I was correct. Oh.
you are correct, and I am wrong, but I'm wrong in a very correct. No, I am wrong in a very correct way. I'm wrong in a very right way.
No, it's okay.
No, just saying that the reason is I was referring to the other paper by Ivanov, right, in which he does dimension 7 and 8.
Then, yes. In this case,
and then in that case,
in dimension 7, I remember that is weaker. You're right.
7 and 8, yeah.
I think so.
Great. So thank you, Mario, for pointing this out. And I'm glad I made the mistake because it gave us an opportunity to clarify the difference. Also, Anna, I have a question for you.
Yes.
So Jason and I have been working on a solution to the G2 Strominger system on transverse Calabi-Yau 7 manifolds.
Mm-hmm.
Okay. But of course, this problem is also interesting in dimension 8, precisely.
Yes.
Right.
Yes.
And so we are solving this on a S1 bundle, say, over a Calabi-Yau threefold, which is a ciphered fibered.
Yes, right.
Do you think if we get this solution right and finish this preprint, you can do dimension 8 sort of automatically using the same trick, right? Because then you would have a T2 fibration and you could write your same ansatz and just stick it in there.
I think so, probably. I am not sure now. I should think more, but probably you are right.
Right, because you start with something, let's say, real 4-dimensional, you take a Seifert manifold on it, and then you
So you
add
are
on.
thinking about solution in, of course, in complex dimension n bigger than, because the case that we consider was complex dimension 3, right? So you are thinking about this solution for the complex. Yeah, so for the complex Monge-Ampere equation that generalized in higher dimension, you are thinking on that case, right?
Yeah, in dimension 8.
Yeah,
that's right.
Real dimension 8.
Yeah, because we can address the problem in real dimension 7, which is a Seifert fibered manifold over Calabi-Yau threefold.
Okay.
And then we pull back the data from the Calabi-Yau like you did, and then we have to take we take the whole connection, right? We don't take the chain connection, but it's all right because they fit in a family, so you can choose this parameter to get the torsion you like. And then, but then it looks to me that your ansatz could sort of immediately solve the 8-dimensional case, provided we begin with this solution in 7 dimensions.
I think maybe it should be possible. I have to think more, but I think in principle it's possible. Another thing that I didn't mention, but all the people is mentioned when it's talking about Hull-Strominger system is, of course, it would be nice to have a similar thing in the symplectic case. I mean, for symplectic, maybe Mario can say something more about that symplectic case for, let's say, a compact symplectic manifold. And then you take a almost complex structure, which is compatible with the symplectic form, and you ask that the first chain class is 0 of the almost complex structure. If it's any way to formulate this system in the symplectic case, that's something that I saw many times, like to open, but I don't know if for special type of manifold, like manifold with, of course, symmetry like torus vibration and so on, is possible to say something. I think Yau in some of this paper consider that, right? Consider equal, I think, like supersymmetry type 2.
Yeah, but this is for. So this is in the context of. I mean, these are the equations for type 2A and type 2B.
Yeah, and exactly. But there is anything here?
No, because in the heterotic string there is no such A and B models.
Okay,
so
there is
I don't know
way.
I don't know. Maybe there is a mathematical way, but I don't know if it would be physically motivated.
No. Then I know that physically there isn't, and probably there is not also mathematical, because a lot of mathematics is inspired from physics. But the question was just, I mean, to have some analogous of what is going on for compact symplectic with the hypothesis that C1, the first chain class, is 0. Okay, Luciano is saying.
Anna, and yeah, in that sense, do you get alpha prime positive in your solution?
Yeah, alpha prime is positive, yes.
Okay,
alpha
cool.
Prime is positive, yes.
Okay.
But I think Fu-Yau themselves show also that you have solution for alpha prime negative, right? As far as I remember, yeah. I think.
We do too. We do too in the 7-dimensional case. I think it happens, but physicists don't like it.
You can have, yes.
Yeah, physicists don't like it.
Yeah, but for physics point of view, probably it's important that alpha prime is positive, as far as I understand.
Yeah. They completely despise alpha prime negative. Yeah. They laugh at you. Yeah. We've been talking to Erik Svanes, and he says, no, don't tell me about these. These are not interesting.
Yeah,
they're interesting because they're sort of generalized, generalized Mario stuff. That's mathematically very cool.
Yeah, but Mario
physicists hate it.
Related to what you were saying, so one thing you can do if you go to the physical formulation of the equations using spinors, one of the two equations, that one is the so-called Gravitino equation, which is just having a parallel spinor for the Nabla-Plus connection, so the connection with total skew symmetric torsion H. But the second equation is called the Latino equation, and this equation, which is H plus 2 times D of the dilaton multiplied by the spinor equals this equation implies, or is equivalent to two things: the integrability of the complex structure and the conformally balanced equation. So if you drop this Di Latino equation, it means that you will have some sort of Hull-Strominger equations without. So you will have some Hull-Strominger equation for a almost Hermitian structure. The almost complex structure would not be integrable.
Yes.
But you will still have something like a holomorphic volume form, a pseudo holomorphic volume form. So maybe in this case you can impose by hand that omega is symplectic, and still I think you have a Bianchi identity which is not trivial.
I see. No, that would
because what you have in the Bianchi identity is the torsion, but the torsion, if the complex structure is not integrable, the torsion has another component.
I see. No, that would be nice, because in some it's curious, this stuff. Yeah.
Okay.
Yeah. I will look.
Maybe we can wrap up the compliments, and then maybe we can lag on a few more minutes to have a more private discussion, if that's the case. So can you thank Anna again, please?
Thank you, Anna.
Thank you.
Grazie. Enrique.
Yeah.